What's up, calculus students? Uh, New lesson two homework. If you've been watching the video from years ago, I've updated it so that we understand more than maybe the first homework how there's many ways to evaluate integrals, which causes problems for a lot of students. But if we just get used to being ready to do either, and then either you could do both, or one is the way to do it versus the other, that's going to help you out big time when it comes to taking the AP test. What we talked about in class, you could use the human way for hundreds and hundreds of years. If you wanted to evaluate an integral, you could take the antiderivative and you could find the displacement of the antiderivative. And that is your accumulation of your derivative or accumulation of your function. You could also potentially use geometry. If you have straight lines, you could use geometry to find the accumulation of what you have if you have straight lines. The key is what is given to you. Okay, well, I want to evaluate the integral of f prime. This is the graph of f prime, which means if I want to do f of 2 minus f of 0, I don't have f of 2 minus f of 0. I could actually find them by using a sign analysis and by understanding the signs of f prime, by understanding how f is going to increase and decrease. I gave you that f of 0 is 3. You could find f of 2 by looking at the accumulation and then adding it to 3 and then subtracting the values. But really, if you find the accumulation, whatever this number is right here, that's your answer. That's what f of 2 minus f of 0 is going to be. The accumulation of f prime telling you how much you increase. That's what we're going to find. So this could be done, but you're pretty much doing this to get that answer anyways. So just be ready. Here, I'm just going to accumulate f prime from 0 to 2. Understanding we have a triangle worth of area, base 1, height 4, so that's 2. A triangle worth of area, base 1, height -4, so this is -2. And I get the answer 0. However, for the next question, you see the accumulation of f double prime. Now, there are two ways to do this. You could actually think about what would the graph of f double prime look like? And you're like, oh, well, I know what the slopes of f prime are. I could graph f double prime if I wanted to. But instead of doing that, really, you could just say, I want f prime of 2 minus f prime of 0. Antiderivative, displacement of the antiderivative to get your accumulation. And that's the way to do it because that's easily found. F prime of 2 is -4. F prime of 0 is 4. I get an answer -8. Being ready to adjust and adapt based on what is asked of you, what you're given. We'll make things more complicated by going from right to left. Okay, 0 to -3. You could say, oh, that's f of -3 minus f of 0, which is the opposite of f of 0 minus f of -3. That is one way to show that from right to left, it's going to be the opposite of left to right. You guys mostly just kind of understand this from our understanding of motion. If you're going back in time, you got to do the opposite. So if I'm going from -3 to 0, well, that stinks. All right, well, let's split this up into two trapezoids. I have a trapezoid base 1, heights of 3 and 6. So that's 9 halves, 4.5. Then from -2 to 0, I have a trapezoid base 2, heights of 6 and 4. So that's 10. So 10 plus 4.5 is 14.5. Going backwards from 0 to -3, I'd get -14.5. Cool. That is what we should do here, because we have the graph of f prime, let's just look at the area under f prime, making sure we're ready to go backwards. But if I'm giving you f double prime, well, it would make sense to use the antiderivative and say, oh, that's just f prime of 0 minus f prime of negative 3. It goes back to, and it's so important, and I'm going to make a video just talking about this. This accumulation of the derivative tells us how much we're going up or going down for your original function. The sign of the derivative tells us f is going up. The accumulation tells us how much we're going up. You can either find the accumulation and add it to f of 0 to get f of 3, or you could take f of 3 and subtract the accumulation to get f of 0, or you take f of 3, subtract f of 0 to find the accumulation. It's this whole triangle of stuff that works. That is calculus. So anyways, f prime of 0 is 4. F prime of negative 3 is 3. So that's 1. Now, options when things get more complicated. What are they? What should we do? Well, again, there's two options. You could just take the antiderivative. I haven't been including plus c's because we know the plus c's are going to go away. If this is like a c and this is like 5 plus c, well, who cares? This is just 5, right? The problem is I don't have values of f, so like plugging in 0 and plugging in negative 3 aren't going to help me because I don't know values of f easily. I could find them, but I don't have them easily. So instead, geometrically. Now, geometrically, sometimes it's beneficial to split this up. We could have done it earlier, like the antiderivative of f prime is f, the antiderivative of 3 is 3x. I could have split those up, but here, geometrically, it's even more beneficial to split things up. That way you understand what's going on. Okay, I have f of 0. I don't want f of 0. I could find f of 0. It's given to me. But really, accumulate f prime from negative 3 to 0. From negative 3 to 0, I've already accumulated it. It's 14.5. But what am I adding? Not just 3. I'm adding a total of 9. Now, how do you find that? This is an option where you have both ways to find this integral. 3 is just a straight line, y equals 3. You could do it geometrically. You have a height, y of 3, over the base length of 3. I get 9. Or you can do this using the antiderivative by taking the antiderivative. Don't worry about the c because it's going to just go away. Plug in 0, subtract negative 9, you get positive 9. So boom, add 9, 23.5. Okay. Ready to split things up. Here, same deal. Since this is f prime, if I took the antiderivative of 3f prime, it would be 3f. This antiderivative would be x squared. Unfortunately, since I don't have f values so readily available, I could find them. It's probably better to do this geometrically to accumulate f prime times 3. Now, this is important. What if we have this constant in front of the function, like 3f prime? Well, if you think about if we want to accumulate 3x squared, you could just take the antiderivative and you'd get x cubed and find the change in that from 0 to 2. Well, if I pulled out the 3 and just kind of not worried about it, and I took the antiderivative of just x squared, I would have 1/3 x cubed. But throwing this 3 back into place, that 1/3 and the 3 are going to go away. So these are equivalent. They're equal to each other. We're good. So for the antiderivative method, it doesn't help us to pull the 3 out. It's worthless. But for a geometric method, it's actually advantageous to pull the 3 out, because then I don't have to worry about multiplying f prime by 3 and then accumulating it. Rather, I can accumulate f prime, multiply it by 3, and I'm good. So like from 0 to 3, oh, that's annoying. I got 0, so I really just have to find 2 to 3, which is going to be 3.5. Negative 3.5. We could use a trapezoid. This is 1/2 a base length of 1, heights of -4 and -3. So this is -7. That's -7/2, -3.5. So I'll have 3 times -3.5. Right? I don't have to worry about multiplying the f prime values, like extending the graph, vertically dilating the graph. Not necessary. Now, here's another example of like, you could do both methods. You could actually do this using the antiderivative, or you could use geometry because 2x is just a straight line. Y equals 2x, just looks like that. So I could just like find the area of the triangle. Probably what I saw a lot of students be more willing to do is take the antiderivative. And then plug in 3 and plug in 0, and you'll get 9. So this is -10.5 minus 9, -19.5. Okay, so like taking the antiderivative is good. If you wanted to use the area, base of 3, height of 6, 1/2, it'd be 3. We'd still get 9. It's like there's ways to do things that are great. If this was just if this was x squared though, if this was like x squared, if this was x squared, you can't use geometry. It's a curve. You have to take the antiderivative or use your calculator. This isn't. So it's f double prime. I'm thinking about what would I get if I took the antiderivative. Now, it's very important. The antiderivative of 3x squared is just 3 times the antiderivative of x squared. That means the antiderivative of 3f prime or 3f double prime is just 3f prime. A lot of people think that this 3, you got to take the antiderivative of 3 and you get 3x. No, you don't take the antiderivative of the 3 here. No, like you just leave it. It's a constant. Whenever you take derivatives, don't worry about constants. Whenever you take antiderivative, don't worry about constants. They just stay there. So the antiderivative of 3f double prime is 3f prime. The antiderivative of 2x is x squared. And I'm actually just going to do that because I know that I have those values. So I got 3f prime of 3 minus 9 plus c, which I don't care about. And then I'm going to subtract 3f prime of 0 minus 0 plus c, which I don't care about. So I really just have to figure out this and then subtract 3f prime of 0. F prime of 3, 1, 2, 3 is -3. Minus 9, so I have -9 minus 9. F prime of 0 is 4. So I get 12. So I get -18 minus 12, which is -30. How do you find the average of something? Well, you can accumulate that something and then divide it by the interval at which you're accumulating. This is how we find averages. It is an average rate of change of f is an average f prime because the rate of change of f is f prime. But boom. -4 to 6, huh? Great. Well, we've kind of already done this. This is 14.5. That's 0. That's -3.5. I got to find the rest of this area. Well, I'm going to not split this up anymore and just think of this as a triangle. Base 1, 2, 3, 4, height 1, 2, 3, 4. So this is -8. So I have 14.5 here. Zero minus 8, so 6.5. Which is 0.65. If I wanted to change that into a fraction, I could, but I don't want to. What's the average f double prime? Well, to find an average, I could accumulate what I'm trying to find the average of from -4 to 6 and divide it by the interval. Well, Using geometry doesn't help you here. I mean, you could graph f double prime. You actually can graph f double prime because you see the slopes of f prime or f double prime. You could create a graph of f double prime and accumulate it, but it's actually easier if you just use an antiderivative. This kind of shows you that the average rate of change of f prime will give me the average f double prime. F prime of 6 is 0. F prime of -4 is 0. This is going to be 0. 0 minus 0 over 10. All right. This is the graph of G. Great. I'm changing it up on you. Like, be ready to adjust and adapt. Okay. 4 to 0 of 3G. Okay, well, I'm going to just like immediately flip things and be like, all right, I want 0 to 4 of 3G. Take the opposite of it. Okay. What do I have? G. What can I find? The accumulation of G. I know this is a curve, but I'm going to be very specific with a semicircle and 2 lines. So what I'm going to do, pull out that -3. I don't want the antiderivative of G. I could use like 3 big G, but I don't have big G. And it's actually going to be extremely hard to find what big G is and big G's values because of the semicircleness. It'd be hard to find G prime as well. So anyways, just keep it simple. What's going to make sense? Just to take -3 and multiply it by this area. This is a semicircle, radius 2. So it's 1/2 pi r squared. So that's 4 pi. That's 2 pi. That's -2 pi. I know a lot of you are like used to having semicircles with radius 2. It won't always be radius 2. You know who you are, who are like on your test thought that the semicircle I gave you was a radius 2, but it wasn't. So -2 pi times 3 is -6 pi. Take the opposite of it, you get +6 pi. Cool. Okay, this is G, the antiderivative of -3G. If I wanted to go with that approach, it'd be -3 big G. I don't have big G, so I don't want to use this antiderivative approach. Rather, kind of want to use the geometric approach. What's going to be beneficial when we're using the geometric approach is to split things up, where it's like you're thinking about taking the antiderivative of both of them separately, which is what we do. You take the antiderivative of -3G, it's -3 big G. Antiderivative of 2 is 2x. We're not going to take the antiderivative. Rather, we'll just find the area from 4 to 7, split this up into 2 triangles. This is a trapezoid, heights of 1 and 2. So this 1/2, base of 1, heights of 2 and 1. So that's 3 halves, that's 1.5. So from 4 to 7, I got 3.5 times -3. So -3 times 3.5, which is negative 7 halves times -3 is -21 halves. 10.5. Yeah. Either take the antiderivative or just think about the straight line y equals 2 from 4 to 7, 6. Okay. Oh, same looking question as above. Same looking question as above. But what's different? They say accumulate G prime. It's going to be very hard to graph G prime, so I don't want you to do it. Rather, use an antiderivative. Now it's going to be helpful to you. It's really the key to the lesson, is like being able to adjust and adapt and do either method. First things first, I'm going to find the integral from 0 to 4, and then I'm just going to take the opposite of that value. Or if you wanted to, you could go straight to like the antiderivative of G at 0 minus the antiderivative of G at 4. It's going to be the same as if I take that 3. Again, I'm going to pull this out. Or if you want to take the antiderivative of 3g prime, it's easy. 3g prime's antiderivative is 3g. That's fine. Plug in 0 and 4. You get 3 times g of 4 minus g of 0. Again, I'm flipping the numbers, so I'm going to take the opposite of this answer. It'll be this answer. Opposite will be this answer. Let me just show you. G of 4 is 0. G of 0 is 0. Oh, what a horrible question, Mr. Mester. I should have done from 0 to 6. But maybe I just wanted to just show you that you can get 0. So the answer is going to be 0. And if you did it the other way, g of 0 is 0 minus g of 4, which is 0 times 3, you're going to get 0. This one's going to be different. So I'm going to take the antiderivative. The antiderivative of negative 3g prime. Don't take the antiderivative of negative 3. Just leave it. It's negative 3g. Antiderivative of 2, 2x. You have a plus c. I don't know how you need it. Find the change. This is the whole values subtracted gives us our accumulation. This is the fundamental theorem of calculus. You could split this up into multiple parts if you wanted to. If you split it up into multiple parts, it actually could have been easier done. You could have just said, I got negative 3g, which I'll find the change from 4 to 7. And then I just have 4 to 7 of 2, which is 6. So like you'll get that 6 there. 14 minus 8 is 6. We still have to do the negative 3g of 7. G of 7 is 1. So however you do it, use parentheses because we're subtracting this. Or if you split it up, you're going to get that 6. G of 4 is 0. So we get negative 3 plus 6, which is 3. This is G, I have G. This is G prime, I don't have G prime, I have G. Splitting this up, accumulating the graph that I have, helpful. Splitting this up, maybe, or just taking the antiderivative, finding the change. That's going to help us. Now we have stuff with G for the one on the right. Here we're just going to accumulate G from 4 to 7, 3.5. Do you want to accumulate X from 4 to 7? It creates a trapezoid. Like I could, if I wanted to, think about Y equals X from 4 to 7. I could use geometry to find this, but I'm probably going to actually take the antiderivative and use that. This one's easy enough for me to just do in my head. Height of 2 from 4 to 7. Let's see. I'm going to have heights of 4 and 7 over a width of 3. This would be 1/2, 3, 4 plus 7. So this is 11 times 3 halves. This is 33 halves. I just found this area geometrically. Let's find the area non-geometrically using the antiderivative. If I plug in 7, I get 49 halves. If I plug in 4, I get 8 or 16 halves. I'm going to keep it as 16 halves. 49 halves minus 16 halves, boom, 33 halves. Get the same thing. 33 halves is what? 16 and a half? No. Yeah, 16 and a half. 26. But over here, plugging in 7. Now, honestly, it's probably going to be better to split this up because like 2 of these 3 are going to be easier to calculate. Like I already calculated this, whether it's using geometry or using, it's easier to split this up than having like a very long antiderivative. So like maybe even this is helpful even if you're going to use the antiderivative all the time because it's just easier calculations. Like that answer's 6. We found this answer already was 16.5. This is g of 7 minus g of 4, which we found earlier. G of 7 is 1, g of 4 is 0. So this is just 1 minus 0. So this is 23.5. It's the average g from 0 to 7. That. Or accumulate g and then divide by 7. Or divide by the interval. This is g. The accumulation of g is 3.5 minus 2 pi over 7. What's the average g prime from 0 to 7? Well, accumulate g prime over your interval. This will give you the average g prime. I don't have g prime. So I realize, oh, this is g of 7 minus g of 0 over 7. G of 7 is 1, g of 0 is 0, so this is 1/7. All right. A couple more, then we'll finish off with the behind-the-scenes calculator edition for like how your calculator actually evaluates things. A little bit of puzzles with integrals are these questions. These questions are kind of tricky. Like, I need you to try them because if you don't try them, you won't realize how tricky they are. You'll think that they're easy. Many of you will just copy down these answers. But like, try to get these answers. I got a lot of stuff here. I got stuff about H, F, and G, H minus G. Woo! I'm going to like tidy them up first of all. I got 2 to 5, 5 to 7. I got 2 to 10. Okay, that's good. So 2 to 5, 5 to 7. So that means I have 2 to 7 of F, which is going to be 2. If 2 to 10 of F is 7 and 2 to 7 F is 2, I know that 7 to 10 of F is 3. No, it's 5. I don't know why I thought that. That way, like 2 plus 5 is 7, or you could just like subtract to figure that out. Cool. H, 2 to 10 of H is 6. 2 to 10 of H minus G is 5. Well, like 2 to 10 of H minus 2 to 10 of G is 5. I know 2 to 10 of H is 6. Subtract that, I get 2 to 10 of G is 1 because 6 minus 1, that's big. 2 to 10 of G is 1. Okay, if 7 to 2 of 3G is 12, that means 2 to 7 of 3G is going to be negative 12. Divide both sides by 3. 2 to 7 of G is going to be negative 4. Let's just make sure that makes sense. I got negative 4. Opposite would be 4 times 3 would be 12. So that's good. I got 2 to 7 of G. I got 2 to 10 of G. If I have negative 4, I'm going to have to be plus 5 from 7 to 10. 7 to 10 of G must be plus 5 as well, because 5 minus 4 has to equal 1. Fun little problems. Now that we've kind of done that little bit of like setup work, we can get these answers. All right, I'm going to immediately find the answer from 2 to 5 of what I have. That negative 3 just goes off to the side. Don't worry about it. Don't take the antiderivative of it. You have the accumulation from 2 to 5 of F is 5. Multiply it by negative 3, it's negative 15. Take the opposite of it, you got positive 15. I am going to split this up, 5 to 7 of F plus 5 to 7 of 3. You can take the antiderivative of this, but it's just a straight line. It's just a rectangle. It's going to be 6. 5 to 7 of f is -3. -3 plus 6 is +3. 2 to 7 of f I found earlier is 2. I know 2 to 5. I know 5 to 7. I added them together. 2 to 7 of 3f would be this 2 times 3, which is 6. 7 to 10 of f I found was 5. How did I find that? I found 2 to 7 was 2. I found that 2 to 10 was 7. Well, 7 to 10 has to be 5. If you want to do that algebraically, 2 to 7 of f plus 7 to 10 of f has to equal 2 to 10 of f. 2 to 7 was 2. I don't know 7 to 10. I do know 2 to 10 was 7. Subtract 2 to get 5. All right, I'm going to go ahead and split this up. 2 to 7 of f I found earlier is 2. And then I got 2 to 7 of 2x. You can either use geometry or just take the antiderivative. I get x squared from 2 to 7. I get 49 minus 4, which is 45. So my answer is 47. 2 to 10 of f minus h. All right, well, it's beneficial geometrically, and sometimes just with any integral. If you have a sum, just split them up. Okay, 2 to 10 of f I got is 7. 2 to 10 of h I have a 6, so this answer is 1. 2 to 7 of g, I think I found that, -4. 2 to 7 of f plus g is 2 to 7 of f, 2 to 7 of g, so that's going to be -2. If you want to split this up, you can. If you guys are just copying this down, like, you got to know why I'm getting all these right answers. 7 to 10 of g I found earlier is 5. How did I find that? I found 2 to 7 of g. If you have 7 to 10 of g, it'll give you 2 to 10 of g. I did some work to find 2 to 7 of g and 7 to 10 of g. Is it 2 to 10 is the question? Oh, no. I have 2 to 7 of g. I have 2 to 10 of g. And then I did some work to find 7 to 10 of g. 2 to 7 of g was -4. 2 to 10 of g I found was 1. Therefore, this has to be 5. Add 4 to both sides, you get 5. 2 to 10 of g, got that. Split this up. Six h, 2 to 10, 6h. That's 36. Why? Because I can pull this 6 out. I'm not going to take the antiderivative because I have the accumulation of h from 2 to 10. So I get 36. These are just little puzzles. And then 2 to 10 of 4, you got options. You can take the antiderivative, plug in 10, plug in 2. You could just say height of 4, width of 2, 32. So this is 6. Cool. If I made a mistake on one of those, my bad. All right. Areas. If you wanted to find this area, you could use geometry. That's first one because it's a straight line. Boom. Or you could tell your calculator to accumulate this. Or you could take the antiderivative. Don't worry about the c. Plug in 0, plug in 2, find the displacement. 8 minus 4 minus 0 is 4. Base 2, height 4, I get 4. Okay? Boom, 4, 4, 4. But now, let's go into the behind the scenes. Here is one approach that a calculator could take. They don't take this approach, but this is kind of the idea of like what your calculator does when you type in an integral. It doesn't take an antiderivative. Instead, it has to use geometry no matter if it's a straight line or it's curved line, it's going to be using geometry. It's going to be using an advanced Riemann sum. And here is your expression for your Riemann sum. Okay, summation notation has to start somewhere. Like we're going to say, start at 1 for I, for K, whatever. Go to n objects. We want those objects to eventually go to infinity. We didn't really talk about that in class, but like, boom, you got that. We have heights times widths. We are just going to use rectangles as our example of the behind the scenes what the calculator does. The heights come from y values. The width comes from delta x values. Now, how do you find your delta x's? The width of all your objects. Well, it's however long your base length is divided by how many objects you have. To find however long your base length is, you're going to do this b minus a. What the heck is b minus a? Well, a is your start and b is your finish in terms of your x values. Cool. Where do your y's come from? Your y's come from plugging in x's, very specific x's, into your function, 4 minus 2x, x squared, et cetera, et cetera, et cetera. The first x you'll plug in, the second x, the third x. This is the notation starting at 1 using integers all the way to your nth x. But we need to be a little bit more specific behind that. What are the x's that we're going to plug in? Are we going to plug in -7? Are we going to plug in 20? How does your calculator know where to start? Well, here's where a comes along. So starting point. So I need to definitely plug in A, but I'm not just going to plug in A. I need to plug in more points. I need to kind of go over a little bit. Plug in that X value, get a Y. Go over a little bit more, plug in an X value, get a Y. Go over a little bit more, plug in an X value, get a Y. How much do I go over? I go over a delta X. So I'm starting at A. I'm going to add a delta X. Then my next one will be like adding 2 delta x's. Then my next one will be adding 3 delta x's. My next one will be adding 4 delta x's. You're going to be adding multiples of delta x. Now, how do you get this multiples 1, 2, 3, 4, 5 delta x's? That's where I comes along. I stands for the integers starting at 1 all the way to n. So I'm going to be adding multiples of delta x. Now, what is delta x? Delta x is b minus a over n. So all of a sudden, b minus a over n shows up twice. This is the formula, guys. This is like the behind the scenes, right Riemann sum approach. All you need to do, first of all, understand those are the same, is fit it with your function and repeat. Let me show you. Sum. I starts at 1, goes to n. I want to take approximately infinitely amount of these objects. My function is 4 minus 2x. What are the x's that I use? A, which is 0, plus multiples of delta x. What is delta x? It's my width divided by the amount of objects. So that's 2 over n. Those are my heights times my width. You can plug this into your calculator, into Desmos, and you can see how if you make n large, you're going to get 4, closer and closer to the actual value 4. I'm just going to show you that. Okay. 10 objects, I get 3.6. 100 objects, 3.96. 1,000, 3.996. 10,000, 100,000. A million, a billion. We're getting closer and closer to 4. We never get to 4, which is why the right Riemann sum has some failures. But like if you use an infinite amount of them, which your computer will break if you do it. That's it. So boom, this is a behind the scenes calculator addition. You can't use geometry for this. You can understand that you want to accumulate x squared from 0 to 2. You can get the right answer by taking the antiderivative using the fundamental theorem of calculus to get 8/3. If you wanted to find this value 8/3 using a calculator, behind the scenes, your calculator would do a sum similar to this, where it's taking our x's and squaring them. Those are my y values, multiplied by my delta x's, which is my overall length divided by n. What are the y values you use? Well, you start at a and you add multiples of delta x, starting at 1, going to n. There is the behind the scenes to get 8/3. Let me just adjust this so that it's just that. I times 2 over n squared times 2 over n. I want to get 8/3. Boom, I'm getting closer and closer and closer to 8/3. That's the behind the scenes approach to break Desmos eventually. It's like, stop adding zeros. This is tough for me to do. 8/3, which is 2.666. Cool. I'm not going to actually find this by taking an antiderivative because you don't know how to take the antiderivative of this. Oh, I do know how to take the antiderivative of this. It's arctangent. Yeah, do you remember the derivative of arctangent? No, you don't. Nobody does. So I think actually the value is arctangent 1 minus arctangent of -1. Arctangent of 1 is actually pi over 4. Arctangent of -1 is negative pi over 4. So this answer is actually pi over 2. Watch. Integral from -1 to 1. I don't expect you to know this, so don't stress out if you're like, how did you get arctangent of 1 is pi over 2? Well, if you took AP pre-calculus, you would know that. Cool. But behind the scenes calculator addition, sum of my y's times my delta x's. My delta x's are still 2 over n because this base length is 2. I'm going to use n objects. I'm going to start from my first height and keep going. Where do I start? Well, I want to sum up. My heights are 1 over x squareds plus 1. What goes in here? Well, I want to start at -1 and I add multiples of delta x. This will be a Riemann sum approach, a behind the scenes calculator addition, 1 over parentheses -1 plus I times 2 over n squared plus 1. There. Use 1, 10, 100. I'm already super accurate. 1,000. We're getting closer and closer to pi over 2. Sine is a curve. So like if you want to find the area under one hump of sine, you can't use geometry. Geometry can only be done to approximate it. Instead, you could take the antiderivative, plug in pi, plug in 0, and you actually get an answer of 2. 2, which is crazy. Now, behind the scenes, your calculator would take sine of x values to get y's, multiply it by delta x. The x values start at 0 and add multiples of your delta x. This is a right Riemann sum approach. I'll just show you. Sine of x from 0 to pi Cool. 2. If I were to change this to be the sine starting at 0 plus I times 2 over n. I'm like breaking my computer right now. Not 2 over n, pi over n. Bless me. Even with 1,000 objects, I'm closer to 2. 10,000, closer to 2. 100,000, closer to 2. Boom. Eventually your calculator rounds. Right Riemann sum works really well for a sine. All right, so you're actually responsible for understanding, like, hey, what's actually programmed into your calculator? Well, it's not exactly this, but it's something like this. Your calculator says an integral is a sum. It uses a advanced Riemann sum similar to this to get what ends up being an approximation for your answer. I don't know if you remember, sometimes we would type in an integral to our calculator, and our answer was just like a little bit off. There were some like decimals that were off. That's because it's just doing the best it can to do an approximation. All right, that's it. Mr. Mester's out. Good luck on the SAT, juniors. You're probably not doing this homework anyways.